Now let's have a quick look at a cumulative distribution function. So recall that a cumulative distribution function, as we've seen again in math methods, is where you take the integral of the distribution, which in this case is an exponential distribution, and that will accumulate that distribution up to 1. So it looks at accumulating the area under the graph. And so if you accumulate an area, and we'll just have a quick look at this over here, under an exponential probability distribution, it looks like that. If you accumulate that area, obviously it will start here, but it's going to accumulate. It's going to accumulate quickly at first and slow down, and then asymptote at something, and that something it asymptotes at will of course be 1. So that's what we're expecting to see, whatever that function is, and that is another variant on an exponential function that we could have with some transformations, or it could be as a log, written as a log function as well. So if that cumulative distribution function is equal to the integral between x and 0 of lambda e to the negative lambda t to t, notice here we've swapped out x for t, we put x there. Now we're going to write it as a function of x again, but we had to introduce t, so that was meant to slide down, and we get this. The integral is equal to lambda e to the negative lambda t over negative lambda between x and 0, which of course, and I'm not sure I'm going to have enough space, they will cancel out. I've got negative e to the negative lambda x minus negative e to the negative lambda 0, and that thing will be equal to 1, and it's positive, so I get 1 minus e to the negative lambda x. And that makes sense. If we go back here, you can see that it's saying 1 minus that. That's introducing this gap here. So 1 minus will be 1 minus whatever this height is here. Well, not quite this height, because the function has changed a little bit. It's lost the factor of lambda, but the point is the same. We're subtracting that exponential from 1, which flips it up. So the transformation that take place here is it flips the exponential over because of the negative here, and it subtracts it from 1. So it's basically flipping the exponential, shifting it up 1 spot. So there we go. So there's my cumulative distribution function. Let's have a quick look at example 2. A new type of EV battery has a battery that needs replacing every 8 years on average. If the manufacturer offers a 5-year warranty, how many cars can they expect to replace batteries for per 100 sold? So if we can calculate the probability of a battery need replacing within the 5 years, then we can calculate the number per 100 sold. A new type of EV has a battery that needs replacing every 8 years. So on average, this represents, therefore, the expected value is 8 years, and therefore we want to calculate an exponential probability distribution. I'll write it down. The expected value equals 1 on lambda, so lambda is equal to 1 on 8, and we get f of x, the probability distribution, is equal to 1 on 8 e to the negative 1 on 8 x, and we could integrate that between 5 and 0, and I invite you to do that now if you want to, or we can just look at the cumulative. So we just want f of x, which is equal to 1 minus e to the negative 1 on 8x, but we want to calculate f of 5. That will give us a cumulative value up to 5, and so in this case that's 1 minus e to the negative 5 on 8, and 0.465 or 0.4647 is probably important here. So that's what we're our probability of there being a replacement required under 5 years. And of course, then if we took at 100 cars per 100 cars, then this is 100 times f of 5 will need replacing, which is 46.47, and we say that's 46. Now, we might say that's pretty high. The average is 8. Does that mean that 46 of them will be under 5 and only 4 of them between 5 and 8? And the answer is yes, and it's actually fairly reasonable. If you have a look at our probability distribution function, where's one I've drawn? Here's one I've drawn here. It's decreasing over time. So if 8's here and 5 is here, well, because of the steepness and because most of the data is going to be in here, if that's the model these batteries have, well then 46 could certainly be in the first 5 out of 8 years, depending on the steepness of the curve. So that is fairly reasonable, and of course we can check it as well through our application of Desmos. So here's Desmos here, and I can change my A to be 1/8, which is of course 0.125, and I can change my upper boundary here to be 5, and we get that answer. So there's my value there, and that shaded region there would represent 0.46. So if you have got your calculator, you can check that quite easily. And example 3 before we finish. Determine the median of an exponentially distributed random variable with a rate of lambda. So the rate is another way of saying the value of lambda. So if it's an exponentially distributed random variable, then we get f of x is equal to lambda e to the negative lambda x, and that's for, of course, x is greater than 0, and it's for x is less than 0. It's otherwise it's just 0. But we're trying to find the median. So the median will be the value where 50% of the data lies below the median. So we're looking at, for what value, there's two ways of doing this. One would be, for what value a to 0 does the integral of lambda e negative lambda x dx equal 0.5? Or 2, for what value does the cumulative distribution function x, but I'll call it f of a, for what value of a does that equal 0.5? And of course the cumulative distribution function is 1 minus e to the negative lambda x. What does that equal? 0.5. And I might do it this way because it's a little bit easier. We're basically looking for the 0.5 mark of our exponential distribution once this is rearranged. So I get negative e to the negative lambda x equals negative 0.5, which gives me e to the negative lambda x equals 0.5, which gives me, I take a log of both sides, negative lambda x equals, and of course this is f of a, so I should probably whack an a in there instead of an x, equals the natural log of a half, and that a is really small. There we go, a, not a subscript, and then I divide by negative lambda, and I get a is equal to negative 1 over lambda log of a half, whatever that value is. So our median for the last example will have been, first of all, log of a half, which is equal to negative 0.693 times by 8, or times by negative 8 because it's 1 over 1/8, and we get a median a value of 5.5, put a line here, for 5, where lambda is equal to 1/8, and that's good because we got 46% of the data was lying below 5, so 5.5 is the median, and that's where the extra 3 or 4 have gone. So we did talk earlier about the mean, and the mean was actually displaced in my conversation. So there's example 3, a bit more general, and you can now do exercise 12e. All the best.